A boat leaves the dock at 2 p.m. and travels due south. So we are at a particular location and the boat is traveling south. Another boat has been heading due east at 15 kilometers per hour and reaches the same dock at 3 p.m. So at 2 p.m. this boat is about to leave. Right, and there's another boat far out here that's approaching it from heading towards east, right? So you make right east. So we're going. This is the motion of the two boats, okay? And reach the same dock. So at 3 p.m. At 3 p.m. is this. Here's the dock still. The first boat is way down here now, and this one has reached. So in somewhere between 2 and 3 p.m. Okay, here's the dock. So here, let's say something like this. This is, let's say, let's name these boats, okay? Boat A and boat B. Okay, at some point, it's gonna look like this. This is almost arriving, somewhere in the middle of arriving, and this is somewhere in the middle of traveling south. So we want to know, when is this distance here the shortest? The distance between the two boats. That's the question. Let's call that S.
Wait, you're trying to find the shortest distance?
Yes. Shortest distance, okay? We typically use the letter S instead of D because we want to use the Lebanese notation. You know how if you write D, then it becomes dd over dt, right? It's weird. So we usually write S for this. You use S of the distance, okay? And in physics, it's pretty popular too, I think, to use S. Okay, so when we set this up, right? If you're not sure like exactly what it is that you're supposed to get, first label the relationship you see here. What geometric relationship are we talking about here? In this shape here. It's a Pythagorean relationship, right? So let's call this, let me call this X, and let me call this Y, okay? Okay, and we know this. X squared plus Y squared must equal to S squared. Okay, and ultimately we want to optimize S. So really, we need to optimize this, right? Optimize. But right now we have two variables. That's not good. We need to be one variable. But both X and Y depends on another variable. What? Time. X is the distance, right? Now, in this scenario, is X the length X, right? So X is the distance right now. Is the length X increasing or decreasing? X is decreasing because it's heading towards the dock, so it's getting shorter, right? So it tells you that it's traveling at 15 kilometers per hour. It's gotta be minus 15 t. Okay. In 1 hour, right? So, Chris, you said 1 hour. This boat here, B, arrived on the docks, and it travels at 15 kilometers per hour. So at 2 p.m., this boat B must have been 15 kilometers. So X, as a function of time, must be 15 minus 15t. That makes sense. Everything makes sense there, right? Okay, so now for Y, what about Y? Y, initially there was no distance, but it's growing at 20. Yeah, so 20t. Now, the S squared can be expressed with only one variable. 15 minus 15 t squared plus 20t squared. And what you want to do is optimize it, which is not hard. Okay, so let me call this f at t, a function of t. And I'm going to differentiate the function of t. Like that. This is what you get. And you got to set this equal to 0. And this is a linear. It's a linear function. What is that? 400. Is that 800? Okay. Okay. What is that? Minus 450? Okay, so minus 450 plus 450 plus 800. So you get 1250t is equal to 450, and this is the time. Okay, so it's going to be 45 over 125, reduce more. 9 over 25. This is in hours. Times it by 60 minutes. Reduce. 12, 5. What's 9 times 12 over 5? 108 over 5. Yeah, you want to usually say like in minutes. It doesn't make sense. This doesn't really make that much sense. So if you just change this into mixed form, 21 and 3 over 5 minutes. This is better. It's 21 minutes. And I don't know, this is about 40 seconds, right?
Past 2, right?
So basically it's around approximately 2:21. They have the shortest distance. Okay, that's what it means. Actually, we should round up. Approximately 2:22, they have the shortest distance.